Alrighty, we will get started in just a few minutes. We'll give everybody some time to join. So hang on one sec. Okay, we might get started. And as people sort of straggle in, I can start introducing what the seminar is about. But thank you everyone for coming. This is our third ever BCI Society's Industry Academia Seminar Series. The purpose of this seminar series is for those of us working in neurotech and BCIs, as we see the space sort of expand to include people in academia and also a lot of endeavors happening in industry, we wanted a seminar series that could sort of reflect this. And for a lot of trainees, PhD students and postdocs that are interested in understanding both of these spaces, we wanted to create an opportunity where you could ask questions to understand sort of what these career paths are like, but also understand the nature of the work happening in these spaces. So we're very excited to be having our third one. Some house rules about today's seminar. It will be 1 hour. We will start with Silvestro's talk, which will be about 20 minutes, and then we'll do a 10-minute Q&A for Silvestro. After Silvestro, Dan will speak for 20 minutes, followed by a 10-minute Q&A for Dan. And I would encourage those in the Q&A to ask questions, not only about the research that they're both doing, but also specifically about their career paths and any advice you might need or have about exploring a career in both of these spaces. But let's get started. So I am very excited for our two speakers. Our first speaker will be Professor Silvestro Masera. Silvestro is a professor of biomedical engineering at EPFL and SSSA. Silvestro has a very multidisciplinary research background. He does a lot of work in not only neuroprosthetics, but does a lot of work specifically with restoring sensory and motor function in disabled individuals. He's going to talk a little bit about that work today, but feel free to ask questions in the chat below. But without further ado, I'll turn it over to Silvestro.
Thanks a lot. Thanks for inviting me. It's really a great pleasure to be here. Let me start with a disclosure, which is kind of related because I'm also sharing, I have shares of companies created on the technology I'm going to show you. Just to start immediately saying that, of course, you can make business also starting from purely academic long-term research ideas. In particular, what we do in my lab, I mean, you can call it as you wish, neuroprosthetics, neurobionics, it doesn't really matter. The idea is what we try to be is the bridge between basic science, mainly neuroscience, but also, for example, material science for new electrodes, new implants. I'm going to be back to this at the very end, and the clinical world. So the idea is to create a bridge and to bring as fast as possible basics discovered in different applications to the clinical, really translational application. We've been working on many different kind of applications, ranging from, this is Elvira, a former student of mine. She's now assistant professor in Pittsburgh, and she's using the exoskeleton developed by a colleague of mine in the long term for stroke neurorehabilitation. We've been working together with Grégoire Courtine for years on restoring locomotion using spinal cord stimulation. You're going to see at the end human augmentation and so on. However, if you name my first dream, is of course this guy. I do hope that you all know is this guy and what happened to his end. Otherwise, guys, you have a problem, if I may say, from my viewpoint. But the idea was really to restore the same kind of dexterity, control, sensory feedback, embodiment that Luke Skywalker is showing in this movie. And we've been working a lot on this topic. In particular, I will mainly focus on the sensory part, but for the sensory part, we have been looking at the possible peripheral interface. We can discuss later why in amputees peripheral, why it makes more sense to me, but maybe later. And in particular, after a lot of going up and down in this chart, in this plot, we identified time electrodes as a good trade-off between having a technology which is reasonably invasive, which can go then to patients for a real translation, but at the same time, quite selective. And the selectivity, could simply be my sudden ability to talk only to them and nobody else listening. So create just a one-to-one connection with one small fascicle, such as the brain does every day. We developed it with my long friend and collaborator, Thomas Stiglitz. And the idea is pretty simple. You enter with a tungsten needle inside the nerve transversally, and you leave inside a polyimide electrode with different active site, metal ones. And then when you stimulate, you can activate different parts of the peripheral nerve. Here you can see while I talk the implantation. It is reasonably simple. And after some preliminary testing, what we did was to have our first implant done in Rome with Paolo Rossini, a colleague of mine and a neurologist and a friend, now I would really say after 20 years. And we implanted a Danish patient approximately 10 years after the amputation of the left hand at the transradial, at the forearm level. And here you can see what happened when it happened when we had what we call the magic moment, when you start stimulating. And he was referring different kind of sensations in different areas of the phantom hand. The hand is no more there, but the beauty of the stimulation, also in other cases, is that you can trick the brain. And then the brain can feel that something at the hand, which is not there anymore, is still happening. And in particular, changing the position of the electrode, you can change where the sensation is happening on the fingertip. Not only that, if you increase the amplitude, the volume of the radio, pumping up the volume, you can modulate the force that the person is feeling at the different location of the hand. So that was really interesting. Then what we did was to go for the next step. So we asked Dennis to perform a series of tasks. I will be very brief for the sake of time about this, but we asked him to modulate the force. So using a classical, and I believe that Dennis is going also to talk about that, Emg control, we asked Dennis to control the prosthesis, which was sensorized, and then the information from the sensor were translated into electrical stimulation in different parts according to the characterization you saw before. First, he was able to modulate it up and down. He was able to generate different level of force. If you look here at the red arrow, he was even able to adjust in real time the performance. So when there was a mistake, he was able to kind of go back to a different level of force. And compared with the natural hand, the right one, which is still connected, more or less we were reasonably close, but we can discuss later if you want, to the natural situation. So in some way, to summarize it, Dennis was able to use it in real time in a way which was similar to the natural one. And then we started playing with Dennis a lot. This is Dennis identifying the compliance of the object. He was able also to do that with the shape of the object, always, as you can see, completely blind and acoustically isolated. He was able to get all these kind of feelings. And what was interesting, he was able to do it not at the level of the final force, but looking at the dynamics of the force. So the difference between two fingers, for example, was able to say the kind of object he was, the shape of the object he was grasping, which is really interesting because this is very likely what we all do when we try to grasp an object and we try to understand the shape without looking at it. So it was easy, fast, reliable, and natural in the way it was exploiting it. And then we moved from 1 patient 1 month to 3 patients for 6 months. Here you can see some of the testing, in particular with fragile objects simulating eggs to see whether it is possible not to break it because of the sensory feedback. We moved to a portable situation when the patient were wearing everything in a backpack, moving around. The next step in few months will be to have everything fully implanted. But then, there will be 2 roads if you want, 2 paths. One is to go for the fully implanted and the clinical real exploitation. And then what we are also doing is to understand more how far you can go with the sensation. For example, with Edoardo Danna, who was a student in my lab at that time, and Alberto Mazzoni, a colleague from Pisa, we showed that it is possible to gather position information and tactile information exploited together in real time. We also showed that it is possible to go more sophisticated than the amplitude modulation. If there are, I believe, people with a neurophysiology background in the audience, you know that this is not how we work. We are not just adding, increasing, or decreasing the amplitude of the firing, is more the frequency. So what we did with Schliemann-Bensmeyer is to use the model that he developed, the biomimetic model, to simulate the force generating on a fingertip and then the firing rate of the different natural tactile sensors. We use it in a real experiment with a subject, comparing our simple amplitude modulation with the biomimetic frequency that he was using, or a combination of both. There are 2 combinations because this was asked by one of the reviewers of the paper, but let's say a hybrid solution. And the interesting result achieved also with Giacomo Valle, who was also a student in my lab at that time, was that by combining it, we published it in Neuron a few years ago, by combining amplitude and biomimetic frequency, we have the best performance, the largest embodiment, and a more natural sensation. It's just an example, but just to say that we are just scratching the cover of what we can do. We can do way more with this kind of approach when, and it's going to happen soon for me and other colleagues, this patient will have everything for good at home. It will be possible to do way more in terms of delivering rich, natural sensations. But then the idea, we wrote a paper on modularity and reusing technology for MED a few months ago. The idea was to take the same technology and apply it for other applications. So very quickly, I want to give you a few examples. With Stanisha Raspopovic, who is now a colleague at ETH, and Francesco Petrini, we showed that it is possible to do the same also for leg amputation, just sensorizing the insole with, of the shoes and delivering the stimulation to the sciatic nerve. So conceptually, very similar, the same, but extremely strong in terms of clinical results. We were able to have the patient reducing the fear of falling, the falling event, the metabolic consumption, and so on, and increasing embodiment. So also in this case, the potentials of this approach are really remarkable, even more for many reasons than for the hand. That's why the company we created, Sensars, is now mainly focused on this topic, on the legs, in particular on pain reduction, which is really important for many of these patients. And then with Diego Ghezzi and 2 of my students, Simone and Daniela, we took again the same technology for the optic nerve. We published 2 years ago a paper in Nature Biomedical showing that using this technology, it is possible to deliver sensation to the visual cortex, implanting in the optic nerve, with a lot of diversity in the sensation. Clearly, the rabbits cannot tell much in terms of the kind of sensation, but looking at the cortical activation, it seems that we can really exploit also in this case the selectivity of these intraneural electrodes. And from that, what we are doing right now is to move to simulations and later also to patient implants with the same idea. No, because the advantage of using a technology which is the same of previous applications in humans, of course, as you know, you can speed up also the translation. We are also using the same technology for another application, which is the stimulation of the autonomic nerves for something related, for example, to cardiac control. In particular, with Fabio Recchia, we are developing a technique for closing the loop inside the vagus nerve. So recording vagus nerve activity, identifying specific bad events in terms of respiration or cardiac activity, and then use them for modulating and altering, for example, the activity of the heart. So in this way, the idea would be to have another application, this time for an even larger number of patients, unfortunately, for people who have cardiovascular problems. Finally, the last application I want to show you is motor. So we talk about sensory, tactile, and position for amputees. We talk about sensory vision. We talk about autonomic for cardiac functions, but you can also use it for motor function. So the idea is to use it for end function restoration after spinal cord injury. So in a complementary way to what we have been doing with Gregoire with spinal cord injury. I personally believe that, and maybe I will fight with Marco Capogrosso and Stani and Gregoire about that, but the selectivity you can reach with spinal cord stimulation for single finger movement probably not enough. So what we tried to do was, again, to use the same electrode, the time electrode, with Marion and Ellen and many other people in the lab, and we look at the selectivity. And the results were incredibly interesting. You know, you can see here, by stimulating the medial nerve, the number of muscles you can elicit independently, and the same also for the extension using the radial nerve. Just to give you an idea, in 5 of 7 monkeys we tested, we were able to control independently all the 5 fingers, including the thumb, even if the implant was done very high above the elbow. Okay, so this is really promising. And then what is interesting, of course, what you can do is to test it with the animals in order to combine the different movements to achieve different grasping tasks and modulate the force. And even in this case, what was really interesting was that even fatigue was reduced. Because of the selectivity of the time electrodes, you can have not the perfect situation, of course, this is not possible or very unlikely to happen, but you can modulate all the fingers, the grasping task, but at the same time, you can have a force which can be recruited over longer time. Okay, just a quick video about the force modulation. And then the next step was to see, can we do something closing the loop, bypassing the lesion? So what we call brain-nerve interface. So what we did was to have the animal anesthetized with lidocaine for a temporary paralysis. And then we implanted, before that, we implanted cortical electrodes, and the animal was controlling the stimulation by thinking, by the cortical activity, as we did ourselves and other people before for other applications. And here you can see the result. We were modulating the wrist extension by this cortical activity. You will see the animal, of course, before the damage, the temporary paralysis is able to do everything easily with no big problem. But then, of course, in 1 second, you're going to see that when there is the paralysis, you know, the monkeys are pretty smart animals. They can find their way to play, but the results were significantly less good than in the other case. You know, they can grasp it, but not as good as often as in the other case. While you will see when the animal is able to bypass the lesion by thinking, let's say by cortical activation, if you want to be more precise, the performance were back to normal. Okay, This is extremely important because now we know, you're going to see in 1 second, now we have at the same time the advantage of two technologies potentially already tested in patients, both the intracortical youth array and our time electrode, and we have preliminary monkey experiments, which seems very promising. Here you can see the monkey paralyzed, grasping with the bypassing of the temporary paralysis, simulating the lesion. Of course, it's not exactly the same clinical case of a spinal cord injury, which I didn't want to do, honestly, to the monkey, but is reasonably close to what could happen in a clinical situation. For this reason, we have now the ethics approved, and we are going to go for the Ministry of Health in Italy for human testing. So the idea is that we are going to test in the University Hospital of Florence, implanting 3 quadriplegics to test whether what we found in monkeys, very simply, is going to be confirmed in terms of controllability at different levels, also with patients. Also, eventually combining it, if necessary, with shoulder control with a light exoskeleton, depending on the kind of the patient. So I hope that I convince you that when you find a technology like the time electrode, you can really try to exploit in different directions with a lot of advantages concerning translationability. I want to leave you just with a small hint about what we are also working on, which is augmentation. So the idea is, instead of controlling, restoring the control of 1 or 2 arms in a person paralyzed, why not trying to go for supernumerary arms? So controlling more than 2 arms simultaneously. So for the people who were like me, who read Spider-Man, like Dr. Octopus, you have more than 2 arms to control. There are a lot of problems, of course, in this case. In particular, the main issue is to find the right interface, both for motor decoding and sensory feedback, which is at the same time quite effective in both decoding and feedback, without interfering significantly with the natural control of the natural harm. So that's something we are working on. If you are curious, we had a bit of ideas published in this perspective paper a few months ago in Nature Machine Intelligence. So let me just say a few quick things. I hope that I convince you that modularity is crucial. Intraneural is an excellent solution, which you can exploit in many different applications. And as one of my mentors now this year is 80, Tom Mortimer, told me many years ago, the possibility of playing with the nervous system, I guess we all agree on that among us in this audience, are really unlimited. This is my 20 minutes. Just let me end to say that, also refer probably maybe to what Dan is going to say after me. Clearly, you see more or less the same path for non-invasive and different invasive technologies. I'm old enough to remember that Emg Control was started mainly by the New Brunswick people, Scott and the others, in the 90s, 80s or 90s, at least with more engineering effort. But now it's not only clinically exploited for prosthesis control, for example, but there are also companies working on the non-clinical exploitation. The electrical invasive is, of course, one step back, but it's going to happen maybe in 20 or 30 years, maybe more, when the technology will be significantly less invasive to go also for non-clinical applications. But what I want to emphasize, I wrote a news and views for Nature Material, which is going to be published, I guess, in a few weeks, in the next issue. We have also to start working more and more on non-electrical interfaces, because clearly, the electrical ones are going to reach kind of the hype of clinical exploitability more or less in 20 years. I don't know when I'm going to retire. That's more or less my period of thinking I can offer you. But at the same time, they will not be perfect. So working on non-electrical, magnetic, ultrasound, and these kind of things could really be the next hype in the field. And with this, I apologize for being a bit late, and I do thank you for your attention. Thanks a lot.
Thank you so much, Silvestro. So many things to ask. So for the attendees in the audience, feel free to type any questions in the Q&A. I can kick us off with a question. So with the nature of sensory feedback, with the goal being to provide naturalistic feedback, right? With a lot of what you're doing with the time electrodes, and I also think of Jennifer Collinger's work and Robert Gaunt's work happening on the cortex with providing stimulation. What do you think are the primary limitations with both of these areas, whether it's in the periphery or providing stimulation to cortex, to ultimately give a user naturalistic feedback?
You know, it depends on what we mean about naturalistic. If we mean that the sensation will be really the same kind of sensation, then very likely the limit is the electrical stimulation. So just going back to the last slide I've shown, because if you try to do that, even a very simple, very selective electrode like the time electrodes are not able to stimulate the different type of the different fibers previously connected to different type of natural sensors in a very selective way. You know, you can do something, and maybe it's better than a cuff electrode. Somebody would kill me for that, but that's my personal belief, but not enough. So if you think about the natural exploitation, I would say that more or less what I show you, and I was talking this morning with Sliman about what he's doing for the cortex, more or less the same approach of the hybrid by biomimetic frequency and amplitude can help also in the cortex. You can reach a lot of good results, but to say, okay, I'm getting the same quality of sensation, you need to go to something more selective than electrical stimulation. In both cases, I would say.
Yep, makes sense. All righty, in the Q&A, we have a question from Elena Amaruso. The question is, what is the mechanism by which sensorized prostheses can help with pain?
That's a very important question. In general, the idea is that because the brain is not getting any more the used peripheral information, because there is no more the hand, what happened is that the brain got bad plasticity, bad connections, and this generates pain. The moment you restore this loop, the sensory motor, the sensory feedback, the brain said, okay, now we are back to normal, something okay is happening, and there is a reduction of the pain. I mean, this is the engineering explanation, but this is more or less what is happening, to the point that when you stop doing it, after some time, it depends on how much time you did it, the pain goes back to the previous situation. So you need to provide information to the brain, otherwise the brain is not happy.
Next question from Lena Teichman. Very interesting talk, thanks. Is there an effect of time-sense amputation injury on the effectiveness of the interventions? And maybe you could speak a little bit on that, to the state of the nerve sort of after amputation.
There are, of course, very important, both. I mean, if the nerve is damaged, you get a limit intrinsically. We had, of the 3 patients I mentioned at the end, one got the implantation 30 years after the amputation. And at the very beginning, it was really bad, because she was not able to refer to us, to refer any sensation on the hand. They were mainly on the stump. And then over time, the sensations moved to the hand, most of them. So something like you're removing dust from the channels, if you want. But the message was that even after 30 years, it is not only me. I mean, Ken Orch, Dustin Tyler, all the other people more or less had similar cases. It works. So it's not a problem. The difference is, of course, in the nerve. The third patient, Loretana, had a damage at the medial nerve because of the, say, amputation. The kind of amputation was removed a bit. We were able to use it, also the medial nerve, but less than in the other cases. If you want, it is expected. If you rely on something and if something is a bit damaged, but also in this case, she was able to do all the tasks, the force control and these kind of things. So it works a bit less.
Makes sense. One more question in chat, and then Dan, if you would like to ask the last question, feel free. Rafa Tucciarelli is asking, what type of feedback were the patients reporting when using this type of technology? Was it, quote, natural to use it after training? Were they happy to use it?
So there are, let's say, the kind of sensation is often tingling, electricity. Very rarely it's really touch. So if you ask a subject, it is a touch sensation similar to the other end. In general, they are unilateral amputees. In, let's say, only 10, 15%, maybe 20, but no more than that, they say, yes, is a touch sensation. In the other cases, is more electrical. You can improve it by combining the two stimulations. But so if they rank it between 1 and 10, and 10 is the really natural one, you can go from 2 or 3 to 5 or 6. But again, the electrical stimulation is clearly limiting. But at the same time, they are very fast in using it. It depends, but I would say most of the patients after less than 1 hour can master it, can get it very easily. And if you choose the right channels, it's not disturbing. It could be reasonably pleasant if you want.
Great answer. Dan, do you have a final question?
Yeah, be happy to, Silvestro. It's amazing. You know, the body of work over these years and its progression is remarkable. Well, one thing I'm curious about, how do you think about, you know, the last question was about how natural is the sensory feedback, but another way to think about it is how actionable is the sensory feedback, and particularly in patients who are highly committed to train with the system. It might matter less whether it's natural relative to pre-injury versus rich and discernible with the information content to functionally get feedback to perform motor output more effectively. How do you think about that?
Let's say, of course, the more useful, the richer it is, the better, the more usable it's going to be by the subjects, and the more likely is that the subjects are going really to use it. Because clearly, you know, what you said is, you are totally right. These are very extremely motivated subjects. So when you enlarge, we were careful in choosing patients with different characteristics, not good. 30 years after the amputation, some damages, to see whether it was, but in any case, they were really motivated, no doubt. And I think at the same time, the more they're going to realize that there is a real advantage functionally, the more they're going to use it. This is in particularly true, for example, for the legs. Clearly, these guys were super happy because they were able to go faster, reducing the metabolic consumption. So the more there is a real advantage in life, but that's something you want to see, we are going to see only with the real test at home, which hopefully is going to happen next year, the more they're going to use it. But at the same time, if the feeling it's really disturbing, you know, some other colleagues, which I do respect, they often say, okay, if it's really useful, they're going to use it not whatsoever, even if it's really disturbing. I'm not really sure, unless it's really super useful. You know, it's a trade-off. If it is useful, I use it. But if it's a bit disturbing, then in the long term, maybe no. So that's why I'm so concerned about increasing a bit more the level of pleasantness of the sensation, because in the long term, this could also be the key for a real use. I don't know if I answered. We'll see. But clearly, you know, going back to the issue of electrical stimulation, you can play a lot with biomimetic and these kind of things. We are going to use more sensors, whatever. There is an intrinsic limit. So 10 out of 10 is not going to happen with this kind of approach.
And on that note, thank you so much, Silvestro. We will turn the time over to Dan. Before Dan speaks, for those who do not know Dan, Dr. Dan Wetmore is a neuroscientist and serial entrepreneur who has identified, developed, and launched early stage technologies in neurotech, category defining consumer products, nanotechnology, to name just a few. He currently wears many hats at Meta's Reality Labs, including a research scientist working with also business development and on R&D strategy. But yeah, without further ado, I'll turn the time over to Dan. Really, really interesting, Dan. There are a lot of questions. So we will start with Joel's question. Dan, how did you get plugged into entrepreneurship or even begin to make sense of the space skill set coming out of a PhD? For both speakers, any thoughts on what it might take to for potentially invasive commercial products? So maybe start with, coming out of a PhD, getting involved in all of this.
Yeah, I'll tackle that one. I knew probably 3 or 4 years into my PhD that a postdoc and a faculty path weren't for me. Frankly, I just wanted to have, I did a PhD. It was great. No one read my thesis, not even my advisor. It was good work. I learned a ton. I moved the needle a tiny little bit on what we understand about the cerebellum. But I wanted to have impact and recognized it, a little larger impact, recognized now than 12 or 13 years ago, that the incentives for translating those things are not necessarily in place in academia. I started taking business school and law school classes during grad school, and then I just dived in. I figured I'd done my 10,000 hours in the lab. I need to go make mistakes and learn the hard way entrepreneurially. Got some money to incubate a therapeutics program for Down syndrome, for intellectual disability and Down syndrome at Stanford. We spun that out to a company that, raised, $75, $80 million and ran clinical trials for 6 or 8 years. And then shifted to devices that were a little faster turn, and just kept diving in, built a community. I mean, Hunter having this type of group is part of that. I don't know, hopefully that answers the question, but it's a much longer discussion perhaps.
On a similar note, Jimmy is asking, I'm curious as to what a day in the lab looks like for the neuroscientists involved in this project.
To be honest, it looks quite similar perhaps to folks doing, computational neuroscience in academia, right? We have, essentially what are like lab meetings. We have invited talks. Folks are, I think one of the main differences is how collaborative our team is and the resources we have to support them, right? We have groups of folks that are engaged in a common goal, right? And there's also a team of engineers helping support a common code base that we all contribute to and work on. But a lot of the things that are similar to an academic environment, our colleagues know our work best, and we want critical feedback from them, right? Of course, in a supportive way. So, the folks in the lab are coordinating with teams collecting data sets, defining protocols to collect those, proposing experiments that are hypothesis driven, working deeply to train models and publish notebooks and get feedback from colleagues and present those internally. So functionally similar. I bet we have more meetings.
A lot of questions about the technicalities of the tech. I quite like this question. Dan, what happens in mixed reality when the user needs to cover their mouth while sneezing or adjust their glasses? Can your EMG algorithms tease apart natural behaviors from VR control?
This is we just had a deep discussion about this yesterday.
Yeah, that's from Tamar, by the way.
Oh, hi, Tamar. So, we want our models to be highly sensitive, but we don't want false positives. So having the right data set and the modeling approach is important there. We're talking about how can we collect null data that's not just you at a laptop as a worker, but we're moving to a new space in a couple months that will have like a fake apartment, with like the little kitchen, right? I don't think there's any cooking that's going to happen there, but you know, are you chopping? Are you doing something like that? So we think a lot about that. There's a number of different approaches we can take to reduce those false positives. Some are more expensive and from the user experience or from the compute and power perspective of something you want to be small and efficient. But there's I'm more worried about someone having a false positive typing than covering their mouth and sneezing for a pinch, for example.
And then maybe we do 2 more questions. We're coming up on time. Sriharsha asks, hello, Dan, can you please talk about the haptic glove which Reality Labs is working on? Specifically on why they choose pneumatics over electroactive polymers to provide sensation.
That's a deep technical question that's gonna, I don't know if I can
take too much time.
Well, I don't think I know the answer well enough. So this work is not from the Control team. It's a team that we've collaborated with quite a bit in the past. That's mostly based in the Seattle area. And they were thinking very broadly about haptics and the different, somatosensation is so complex. I mean, this relates to Silvestro's work as well. There are different, essentially they're looking at a lot of different technologies to try to activate specifically different parts of the somatosensory system and sensors.
And then maybe we end with this question. I was wondering if it is possible to get a research position in Reality Labs without having a PhD. So maybe more broadly speaking, can you talk about sort of the different paths that lead people to Reality Labs? And yeah, the type of candidates you're recruiting.
Yep. So our research scientists, like with that official title, here all have PhDs, but we also have, and it's kind of like a hack, research engineers who are working in the exact same way as our scientists on the same teams and contributing in the same way, and just happen not to have a PhD. So that's certainly a path. We have hardware engineers, we have software engineers across the full stack. We have human-computer interaction scientists and research engineers. And then we also have project managers and product managers, a lot of roles that don't necessarily require a PhD, but we tend to look for folks who are technically fluent in a deep enough way in one or more of the relevant subject matters that they can interact with, understand the research process, interact with our scientists and the research programs in the right way. And I'd just say, if you're interested, my contact info is here, reach out. And if we don't get to some of the questions, I'm happy to field them there as well.
Yeah, we do have several more questions, but we are up on time. To end, I do want to say when I was putting together who we wanted to invite for this, finding people that do peripheral interfaces, you both were my first choice. So I'm very grateful that you both said yes. I think your work is very, very exciting and is really on the forefront for what we're learning about creating peripheral interfaces for different kinds of users, whether it's able-bodied people controlling VR devices, or a lot of Silvestro's work working with patients of all different kinds. So thank you both for taking the time. And for all of the attendees, thank you for all of your questions. And yeah, thank you so much.
Thanks a lot.
Hi, everybody.
Thank you, everyone. Nice to share the hour with you, Silvestro.
Nice to see you. Bye-bye.